So in this beam analysis chapter, starting with the example 1, in this example we can see here a beam AD, and this beam is resting on two supports, which is a pin support at point A, and a roller support at point D. So the first step is to determine or to draw the free body diagram. Free body diagram is simply replacing the support with the reactions. As here is a pin support, this pin support will be replaced by two reactions, which are AX and AY. Similarly, at point D there is a roller support. We know that roller support is used to be replaced by a single reaction at vertical direction, which we have denoted as dy over here. We can see an inclined load or an inclined force at point B, which is 12 kip. The angle with the horizontal is 30 degree. So we can determine two components of this inclined load as 12 cos 30, which will be the horizontal component 10.4, and the vertical component will be 12 sin 30, which is 6. From here we can determine the components. So determining the component, we will be using the components to calculate the reactions, and moreover here is another uniformly distributed load acting throughout a length of 8 feet from C to D. Here the value of this uniformly distributed load is 0.75 kip per feet. So the total load will be 8 times 0.75, which is 6 we have written over here. And the center of this load, or the point at which this total load will be acting, is exactly the midpoint of this 8 feet. So it will be acting at a distance of 4 feet from C or from D. As we know that we have 3 equilibrium conditions available, and we can also see here we need to determine 3 support reactions. So using that 3 equilibrium condition, we can simply form 3 equations, and from the 3 equations we can easily determine the support reactions, which is the main objective of this example. So applying summation of moment at point D, we can apply moment at any point, but most preferably at the supports, as we know that at support the moment will be 0. So summation of moment at D will be 0, considering clockwise direction as positive. Now let's see which are giving moment with respect to point D. Starting with this AY. This AY is acting upward. This AY is giving a rotation in clockwise direction, we can see, with respect to point D. So it will be positive AY, as we have considered clockwise as positive. And now this force, while considering the moment means force times the momentum. Here the momentum will be 4 plus 4 plus 8, in total 16. So AY times 16. And then we can see here AX, but this AX is acting towards point D. So this AX will not be having any perpendicular distance or momentum. That's why this AX will not be giving any moment. So we can avoid this AY. This AX, we are avoiding this AX. Now at point B, we can see here 6 kip load, which is acting downward. It will be giving a rotation in anti-clockwise direction, but we have considered here clockwise as positive, so it will be negative 6. And now here the momentum for this 6 kip will be 4 plus 8, which is 12, and then 10.4. 10.4 is acting along this point D, so it will also not be giving any moment. And lastly 6 kip is acting at a distance of 4 feet from point D, and it is also giving rotation in anti-clockwise direction, so it will be negative 6 times 4. And from here we can calculate the value of AY. Now applying summation of f of y equal to 0, considering upward direction as positive, Let's form another equation. You can see here ay is acting upward, so it will be positive ay. 6 is acting downward, so minus 6. 6 is acting downward, so minus 6, and dy is acting upward, so plus dy will be equal to 0. Plug in the value of ay over here, we will be able to calculate the value of dy. Similarly, applying summation of f of x equal to 0, we can see here in this beam the x directional loads or components available on this beam are ax is acting rightward. We have considered rightward as positive, so ax, and then 10.4 is acting leftward, so it will be negative 10 minus 10 point or minus 10.4. We cannot see any other available load or components or load components or reactions, so it will be equal to 0, and from here we will be able to calculate the value of ax. In this way we can conclude the value of ay, dy and ax. In example 2, the loading type is a bit different, and we can see here another external moment is available on this beam AE. And the support conditions are almost same. Here is a pin support and a roller support. This pin support will be replaced by two reactions, and this roller support will be replaced by a single reaction, which is dy. Firstly, denoting the reactions first. Now for this uniformly varying load of 2 kip per feet, firstly we need to determine the total load, as we have determined for this example 1 of an uniformly distributed load of 0.75 kip per feet. But here the loading pattern is a bit different. It is a uniformly varying load, and the shape is just like a rectangle, just like a triangular section. So we will be applying the same formula of triangle's area over here to calculate the total load. We can see this load is acting throughout a length of 3 feet in total, so it will be half times the length throughout which it is acting, which is 3 feet over here, and then the value of this load is 2, so 2. This is exactly the same formula of the triangle's area. From here we will get the total load as 3 kip, so we have written over here. Now we also need to calculate the center point of the point at which this total load will be acting. While considering moment, it will be required. So this load of 3 kip will be acting at a distance of 1/3 of its length from the increasing side. That means the center or the point at which this load is acting will be at a distance of 1/3 of the total length throughout which it's acting. Total length over here is 3. From this increasing side, the distance will be 1/3 times 3, so it will be 1 feet. So from increasing side is 1 feet, and we can see here total is 3 feet. So from decreasing side or from point C, it will be 2 feet. Lastly, at point E, there is a external or there is a point load 6 kip. Now applying summation of moment at D, considering clockwise as positive, we can see at point A, ay is acting upward, giving a rotation in clockwise direction, so it will be positive ay. The momentum will be 3 plus 3 plus 3, which is 9. As we are calculating with respect to point D, so ay into 9. And secondly, we can see here 24 kip feet is an external moment. So while considering the while taking the moment at D, we need to consider the external moments also. It's 24 kip feet. It's giving a rotation in clockwise anti-clockwise direction, but we have considered here clockwise as positive, so it will be negative 24. 3 kip is giving rotation in anti-clockwise direction, so minus 3, and we have already calculated distance from D, which is 1 feet, so minus 3 into 1. And lastly, 6 kip is giving rotation in clockwise direction, so it will be positive 6 times the momentum here. That means the distance of 6 kip's direction from point D is 3 feet. So positive 6 times 3. From here we will be able to calculate the value of ay, which is 1 kip. Now applying summation of f of y, we will be able to form the second equation, ay minus 3 plus dy minus 6 equal to 0, and plugging the value of ay over here, we will be able to calculate the value of dy. And lastly, summation of f of xy, taking summation of f of x equal to 0, we will get the value of ax as 0. Now in this example 3, the loading pattern is exactly same as the first example, so hope we will be able to solve this problem. And the support condition is also same, ax and ay will be coming from this pin support, and for roller support a single reaction dy will be arising. Now the external loadings are 8 kilonewton acting as a point load, 4 kilonewton acting as a point vertical load, and 2 kilonewton as a horizontal load, and 1 kilonewton per meter a uniform distributed load acting throughout a length of 4 meter. The total will be 1 times 4, which is 4 kilonewton, is acting right at the midpoint of this 4 meter. Now taking moment at D, considering clockwise as positive, so ay times 4 plus 4 plus 4, which is 12. Ay is giving rotation in clockwise direction, so it's positive ay. 8 is giving rotation anti-clockwise, so it will be minus 8 times, for this 8 the moment term is 4 plus 4, which is 8, so 8. And for this 4 kilonewton is also giving rotation in anti-clockwise, so minus 4. Here the moment term is 4, so minus 4 into 4. And lastly 4 kilonewton is giving rotation in clockwise, so plus 4. The moment term with respect to point D is 2. From here we will be able to calculate the value of ay. Plugging the value of ay in fy, we will be able to calculate dy, and similarly applying summation of f of x equal to 0, we will get the value of ax. We can see here that the available x directional forces or the reactions on this beam are ax rightward. We have considered rightward as positive, so ax, positive ax, and then 2 kilonewton is acting leftward, so minus 2. None other forces are available over here, so from here we will get the value of ax as well. In this way we will calculate the support reactions. And lastly, for example 4, we can see the support condition is bit changed. A fixed support is given over here. While there was a pin support, 2 support reactions will be replacing this pin support. This roller support condition will be replaced by single support reaction, but in times of fixed support, this fixed support will be replaced by 3 support reactions. One is the x directional one, which is dx. One is another one is y directional one, which is dy, and lastly moment, which has been denoted as md over here. Here we can see an uniform distributed load from this 2 kilonewton per meter acting along a length of 4 meter. Throughout the length of 4 meter, we will get the total load as 8 kilonewton. And from this 8 kilonewton incline loading, we will get the value of components as 4 and 6.93. Now applying moment at D, considering clockwise as positive, so taking moment with respect to point D, 4 is acting downward, it will be giving rotation in clockwise direction, anti-clockwise direction. We cannot see any loading at point A, so we have started from point B. At point B, 4 is acting downward, which will be giving rotation in anti-clockwise direction, but we have considered clockwise as positive, so it will be negative 4, and the momentum will be 2 plus 4, which is 6, so minus 4 times 6. The 6.93 is acting towards point D. It will not be giving any moment, but we have another load available, which is 8 kilonewton, is acting at a 2 meter distance from D. So 8 times 2, it's 8 kilonewton is giving rotation in anti-clockwise direction, so it will be minus 8 times 2. And lastly MD is giving rotation in anti-clockwise direction, so it will be negative MD. From here we will get the value of MD as minus 4 T cube. Now applying summation of f of y equal to 0, we can see that 4 is acting downward, so minus 4, 8 is acting downward, so minus 8, and dy is acting upward, plus 8y. From here we will be able to calculate the value of dy, and similarly applying summation of f of x equal to 0, we will be able to conclude the value of dx as minus 6.93 kip. In this way we will be able to calculate the support reactions or the beam reactions, which will be used in our later semesters to design a particular beam or a structural element. Thank you.